When installing a 4-wire 50 amps feeder to a spot disconnect panel, and a portion of the conduit run consists of rigid metal conduit embedded in concrete, bonding the RMC to the ground wire is essential. RMC is a conductive material. When it is in contact with concrete, it can create a ground path. Bonding the RMC to the ground wire ensures that any electrical faults or surges are safely directed to the grounding system. Here is a breakdown of the bonding procedure. Firstly, expose the end of the RMC where it transitions from concrete to polyvinyl chloride conduit. Secondly, clean the surface of the RMC to remove any dirt or debris. Thirdly, wrap a ground clamp or fitting around the RMC and connect it to a dedicated ground wire. Fourthly, secure the ground clamp or fitting tightly. The ground wire must be sized according to the amperage of the feeder. For a 50 amps feeder, a 6 American wire gauge or larger copper ground wire is recommended. Ensure that the ground wire is properly terminated at the ground bus bar on the disconnect panel. It is also recommended to consider installing a ground rod near the spot disconnect panel for additional grounding. The bonding work should be inspected by a qualified electrician to ensure proper installation and safety. By following these steps, the RMC is properly bonded and the spot disconnect panel is grounded according to code requirements. Understanding the NEC, or National Electrical Code, requirements is critical for safe electrical installations. Article 250 covers grounding and bonding, and sections within this article specifically address the bonding of metal conduits. The goal of bonding is to create a low impedance path for fault current to return to the source. This low impedance path facilitates the operation of overcurrent protective devices such as circuit breakers or fuses, which interrupt the circuit during a fault condition, preventing electrical shock and minimizing damage. When RMC is encased in concrete, the concrete itself can act as a dielectric, which can increase impedance. Moisture and minerals in the concrete can also contribute to corrosion of the RMC over time, further increasing impedance. Therefore, direct bonding of the RMC to the grounding system is necessary to bypass these potential issues and maintain a reliable ground path. The specific type of ground clamp or fitting used to bond the RMC is also important. It must be listed for the purpose and compatible with the materials of both the RMC and the ground wire. Typically, a bronze or copper ground clamp is used for copper ground wires, while a galvanized or stainless steel clamp is used for galvanized RMC. The connection must be mechanically sound and provide good electrical contact. The tightening torque specified by the manufacturer of the clamp should be followed to ensure a secure connection. Regarding the ground wire size, using a 6 American wire gauge copper wire for a 50 amps feeder is a common practice, but it is essential to verify this size against the requirements in NEC Table 250.122. This table provides the minimum size of equipment grounding conductors based on the rating of the overcurrent protective device in the circuit. In some cases, local codes or regulations may require a larger ground wire size, so it is always best to check with a local electrical inspector. The termination of the ground wire at the ground bus bar in the disconnect panel is another critical step. The ground bus bar is a dedicated terminal block specifically designed for connecting grounding conductors. The ground wire should be securely fastened to the bus bar using a listed connector, such as a compression lug or screw terminal. The connection should be tight and free of corrosion. A ground rod can provide an additional layer of protection by providing a direct connection to earth. This can help to stabilize the ground potential and reduce the risk of voltage fluctuations. If a ground rod is installed, it should be driven into the earth at least 8 feet and connected to the ground bus bar in the disconnect panel using a continuous length of grounding electrode conductor. The size of the grounding electrode conductor is determined by NEC Table 250.66, based on the size of the service entrance conductors or the equivalent. Final inspection by a qualified electrician is crucial to ensure that all aspects of the bonding and grounding system are installed correctly and in accordance with code requirements. The electrician will typically perform a visual inspection of all connections, check the tightness of all fasteners, and verify the ground wire size and routing. They may also use the ground resistance tester to measure the impedance of the grounding system and ensure that it is within acceptable limits. Additionally, it is important to consider the overall layout of the spa and its surrounding area when planning the electrical installation. The location of the disconnect panel should be readily accessible and within sight of the spa, as required by the NEC. The panel should also be protected from the weather and physical damage. All electrical components used in the installation must be listed for use in wet locations, and all wiring must be installed in accordance with the NEC requirements for wiring methods in wet locations. This includes using waterproof connectors and enclosures, and ensuring that all wiring is properly supported and protected from damage. In addition to the bonding and grounding requirements, there are several other safety considerations to keep in mind when installing a spa. A ground fault circuit interrupter, or GFCI, is required to protect all branch circuits supplying the spa. A GFCI is a device that monitors the current flowing in a circuit and quickly interrupts the circuit if it detects a ground fault. This can help to prevent electrical shock in the event of a fault. The GFCI should be tested regularly to ensure that it is functioning properly. Signage should be posted near the spa to warn users of the potential hazards of electricity and water. The signage should also include instructions on how to operate the spa safely and what to do in the event of an emergency. It is also important to educate all users of the spa about the importance of electrical safety and the potential risks associated with using electrical equipment near water. Regularly inspect all electrical equipment and wiring for signs of damage or wear. Replace any damaged or worn components immediately. Keep all electrical equipment and wiring dry and free of moisture. Do not use electrical appliances or devices while in the spa. If you are not comfortable performing electrical work yourself, hire a qualified electrician to do the work for you. Electrical work can be dangerous, and it is always best to leave it to the professionals. Remember, proper bonding and grounding are essential for electrical safety. By following these steps, you can help to protect yourself and others from the hazards of electricity. The NEC is not a design manual. It provides minimum safety standards. Following the NEC does not guarantee a safe electrical installation, but it does provide a framework for ensuring that the installation is performed in a safe and workmanlike manner. Always consult with a qualified electrician or electrical engineer if you have any questions or concerns about the electrical installation of a spa. Their expertise can help you to ensure that the installation is safe and compliant with all applicable codes and regulations. When dealing with electrical installations, it's important to use the correct terminology. Here's a brief glossary of terms related to grounding and bonding. Firstly, grounding refers to connecting an electrical circuit or equipment to the earth. This provides a low impedance path for fault current to flow back to the source, allowing overcurrent protective devices to trap and clear the fault. Secondly, bonding refers to connecting together all metal parts of an electrical system to create an electrically conductive path. This ensures that all metal parts are at the same potential, reducing the risk of electric shock. Thirdly, a ground wire is a conductor that connects electrical equipment to the grounding system. It provides a path for fault current to flow back to the source. Fourthly, a grounding electrode is a conductor that is buried in the earth and connected to the grounding system. It provides a direct connection to the earth, helping to stabilize the ground potential. Fifthly, a ground bus bar is a terminal block specifically designed for connecting grounding conductors. It provides a central point for all grounding connections in an electrical panel. Sixthly, a ground fault circuit interrupter, or GFCI, is a device that monitors the current flowing in a circuit and quickly interrupts the circuit if it detects a ground fault. This can help to prevent electrical shock. Seventhly, overcurrent protective devices are devices such as circuit breakers or fuses that are designed to protect electrical circuits from overloads and short circuits. They interrupt the circuit when the current exceeds a predetermined level. Eighthly, impedance is the total opposition to the flow of alternating current in the circuit. It includes resistance, inductive reactance, and capacitive reactance. Ninthly, voltage is the electrical potential difference between 2 points in a circuit. It is the driving force that causes current to flow. Tenthly, current is the rate of flow of electrical charge in a circuit. It is measured in amperes. Understanding these terms will help you to better understand the principles of grounding and bonding and to communicate effectively with electricians and other electrical professionals. The size and type of conduit used for the electrical installation can also impact the grounding and bonding requirements. As you already know, RMC is a metallic conduit that provides excellent physical protection for wiring. It is commonly used in locations where the wiring is exposed to physical damage or corrosive environments. Polyvinyl chloride conduit is a non-metallic conduit that is lightweight and resistant to corrosion. It is commonly used in underground applications and in locations where the wiring is not exposed to physical damage. When using RMC, it is important to ensure that all sections of the conduit are properly bonded together to create a continuous electrical path. This can be done by using threaded couplings or by using bonding jumpers to connect sections of the conduit together. When using PVC conduit, it is important to install a separate equipment grounding conductor inside the conduit to provide a grounding path. The equipment grounding conductor should be sized according to NEC Table 250.122, based on the rating of the overcurrent protective device in the circuit. The choice of conduit material depends on the specific application and the environmental conditions. RMC is generally preferred in locations where physical protection is a concern, while PVC conduit is generally preferred in locations where corrosion resistance is a concern. In some cases, a combination of RMC and PVC conduit may be used, as in your case with the spa feeder installation. In this case, it is important to ensure that the transition between the two types of conduit is properly bonded to maintain a continuous grounding path. The NEC provides specific requirements for the installation of electrical equipment in and around spas and hot tubs. These requirements are designed to minimize the risk of electric shock and ensure the safety of users. Some of the key NEC requirements for spas and hot tubs include the following. Firstly, all electrical equipment installed within 5 feet of the inside wall of the spa or hot tub must be GFCI protected. Secondly, a disconnecting means must be provided within sight of the spa or hot tub. This disconnecting means must be readily accessible and capable of disconnecting all ungrounded conductors supplying the spa or hot tub. Thirdly, all metal parts of the spa or hot tub, including the metal frame, the metal shell, and any metal piping, must be bonded together. Fourthly, a bonding conductor must be connected to the bonding grid of the spa or hot tub and extended back to the equipment grounding bus in the electrical panel. Fifthly, underground wiring must be installed in rigid metal conduit, intermediate metal conduit, rigid polyvinyl chloride conduit, or electrical metallic tubing. Sixthly, overhead wiring must be installed at least 22.5 feet above the maximum water level of the spa or hot tub. Seventhly, lighting fixtures installed above the spa or hot tub must be at least 12 feet above the maximum water level. Eighthly, receptacles installed within 10 feet of the inside wall of the spa or hot tub must be GFCI protected. Ninthly, the spa or hot tub must be installed in accordance with the manufacturer's instructions. Tenthly, the spa or hot tub installation must be inspected by a qualified electrical inspector. By following these NEC requirements, you can help to ensure the safety of users and prevent electrical hazards. The grounding and bonding requirements for spas and hot tubs are particularly important because of the presence of water. Water is a good conductor of electricity, and even a small amount of current can be fatal. By properly grounding and bonding all metal parts of the spa or hot tub, you can help to minimize the risk of electric shock. It is also important to educate users about the potential hazards of electricity and water. Users should be instructed to never use electrical appliances or devices while in the spa or hot tub and to never touch any electrical equipment with wet hands. They should also be instructed to immediately exit the spa or hot tub if they feel any tingling sensation or if they see any sparks or smoke. By following these safety precautions, you can help to ensure that your spa or hot tub is a safe and enjoyable place to relax. In addition to the NEC requirements, there may be local codes or regulations that apply to the electrical installation of spas and hot tubs. It is important to check with the local building department or electrical inspector to determine if there are any additional requirements in your area. Some local codes may require additional grounding electrodes, larger ground wire sizes, or other specific measures to enhance electrical safety. It is always best to err on the side of caution and to install the most robust grounding and bonding system possible. The cost of additional grounding and bonding materials is relatively small compared to the potential cost of an electrical accident. Remember, electrical safety is not something to be taken lightly. It is important to follow all applicable codes and regulations and to take all necessary precautions to protect yourself and others from the hazards of electricity.